Hi everyone, Dr. J here, and in this video we're going to continue talking about structure from motion, and in particular we're going to talk about stereo vision and parallax and how these things help us reconstruct three-dimensional scenes. So what we're going to talk about today is sort of similar to what we talked about in the last video, where you have a perspective center, you have the projection of your three-dimensional real-world object onto this image plane, and the image plane has a coordinate system of its own. And so you can use the location and relief displacement of objects in that and sort of think about it in terms of this geometry and similar triangles to work out things like the height of a particular object if you know the height of the camera, the distance in the image, and the relief displacement. Now the difference here is that now we're going to explicitly account for motion. And so structure from motion, the idea here is that the camera is moving, and so we're getting information from multiple perspectives. So we don't just have one perspective that we're looking at now, we actually have two perspectives, or even better, multiple perspectives that we can use. And the basic idea is given in this diagram, and many of the diagrams, by the way, that you see that look like there's screen pictures of a textbook are actually pictures of a textbook. And this is the textbook called Introduction to Modern Photogrammetry by Edward McHale, James Bethel, and Chris McClone. And this is just have some really great diagrams in their textbook to illustrate some of these topics. And so in some cases I couldn't find an equivalent online, so I just took a picture of their textbook and stuck that in here. And so that's what you're seeing here. And we're all familiar with this example. The example here is you're in a car, you're driving along, and as you're driving, objects that are closer to you appear to move by faster, much faster than objects that are farther away. And so here we've got a tree close to the road and a hill kind of in the distance. And as you go by, you pass the tree pretty quickly, but the hill appears to only move a smaller amount. And this is called, this effect is, of course, from parallax. You have something which is an apparent motion it's an apparent motion of the object due to your own motion. And so if you view an object from one direction and then you view it again from another direction, it will appear to have moved. And this is, of course, how our eyes work. We have two eyes that are set a particular distance apart, and that distance between our eyes allows us to get 3D information about the world around us. 3D cameras or 3D movies, for example, work in a similar way where two different perspectives are given, and you can put on those 3D glasses and it will filter out the image from one of the cameras so the left eye will just see what the left camera saw and the right eye will just see what the right camera saw, and you'll get a 3D view. And a headache in the case of 3D movies in some cases. So this is what we're going to do. By moving the camera along, we'll get information about our scene on the ground. And again, we're sort of thinking about this from the context of UAV imagery. We're flying the drone along, it's taking pictures, and even with just vertical imagery, because we have this perspective view, we're going to end up imaging objects on the ground from two different perspectives. And that's going to be because we're going to define our mission to have some degree of overlap. And we'll talk more about overlap and how much overlap we need and things like that in another video. But for now, we'll just sort of assume that we've got enough overlap, and so that overlap is going to give us these multiple perspectives. And by having more overlap, you can get more of these images to overlap, and you can get multiple perspectives and things like that. So just kind of schematically or conceptually, we've got an object here, and in this case, this is not drone imagery, but just an basic imagery of an object. And we're going to identify points in each one of these photographs. We've taken photographs here from different perspectives, different viewing angles, and we can identify points in the image which are the same point. And we're going to do this actually for a whole set of images, and then we'll be able to cross-reference those points and work out their locations and actually solve for what the overall 3D location is of each one of those points. And we're going to be able to use this for both our ground control points, which we'll be able to see in a subset of our photographs, as well as just generic points in the image. And to do this, the process that is used to generate this kind of a result, an actual 3D coordinate from all these images, we're going to use what are called the collinearity equations, and I'm not going to go into a lot of detail about these because they're pretty mathematical and a little bit beyond what we need for this video. But basically, this is going to be the mathematical foundation for how we relate coordinates in the image plane and coordinates in the object space. So we've got some points out here in the real world. Those are projected onto our image, and these collinearity equations are going to be how we relate the two. And there's some terminology that we need to use. So here's our image plane, and here, of course, here's our exposure center, or our perspective center, as we've been calling it. And we're going to have an image point, and we'll use x, y, and minus f. So f is that focal length. We're going to essentially assume that this exposure center is the origin point for the image. And then that means that our image plane has some x and y coordinate, but then its z coordinate is going to all be the same, just minus f, whatever that focal length is. Then we've got our ground point, capital X, capital Y, capital Z, and that's going to be, we've got these two vectors here, and in order to really constrain these vectors, we need to know the origin, location. We need to know the location of the exposure center. So that's three values, That's three values, three coordinates, x, y, z. And then we're going to need to know essentially three orientations, or three angles. So if we can get this vector identified in terms of its, maybe its x component, y component, and z component, then we can identify the location of the ground point. And we won't be able to do this with a single vector, but by having multiple images that all have vectors pointing to this particular ground point, then we'll be able to do this, and we'll be able to solve for that system. So let me show some math. And again, I don't want to get too far into the weeds here, but basically we've got our image coordinates on the left in this top equation, and we've got our object coordinates, object meaning ground coordinates, on the right. And we're going to relate them through what transformation matrix or rotation matrix. And this is basically the collection of information in those angles. So if I back up here just for a second, this is the angles that we need. So it's like the angle from this axis to our vector here. And so that's all encapsulated in this M matrix. It's a matrix of numbers, and we can multiply a matrix by a vector. That gives us another vector. And so we can do this equation on the top. M is what's called an orthogonal matrix, and so we can actually take the transpose of M, and that's inverses the relationship. And that allows us to go from image coordinates to ground coordinates. And so if we just think about this conceptually for a moment, we want to get image coordinates from ground coordinates. This might be ground control points. We're using our ground control points to sort of reference our image. That might be the top equation. And then on the bottom equation, maybe we know then what our image coordinates is using our ground control, and we can reference every other pixel in our image, and then we can use that to identify ground points. Now that's kind of, we're not quite there yet, but we're going to get there eventually. And so the collinearity equations, more generally, we need to scale and shift these parameters, because there could be arbitrary scales in the origin points of our ground points. So our ground points might be in a UTM coordinate system, for example, and our image coordinates, there might be some offset between the perspective center and what our processing software thinks is the origin of those photographs. There might be a scale factor off, and so we have these additional parameters. We can basically multiply these out, and here I've just multiplied them out, and I've actually eliminated one set of equations. So there's 3 rows in this vector, and that corresponds to 3 equations. I've eliminated one, which actually eliminates this k parameter. And so we've used the third equation to eliminate that unknown, and that leaves us with these 2 equations here. These equations here are relating the object coordinates. X minus x naught is just the coordinate, the x coordinate of the object in that coordinate space. And that is going to be related to the image coordinate, related to its own origin. And then these little m values now are the components of this capital M matrix. So this is the 1, 1, first row, first column of matrix M. And this is a 3 by 3 matrix. I didn't mention that before, but capital M is a 3 by 3 rotation matrix, 3 by 3 for 3-dimensional rotations. And so we've got the 1 row, 1 column, first row, second column, first row, third column, third row, first column, third row, second column, third row, third column, and so on and so forth. And so here on the right-hand side now, you can see this is, again, kind of our ground control point setup. maybe we know these and we solve for what our image coordinates are. F here is our focal length, so that's going to be the same as what we've been using. And we've got x and y there. We can also do the inverse, so we can do some kind of transformed system of equations, and again eliminate the stretch or scale parameter, and then solve for our object coordinates in terms of our image coordinates. And also there's the focal length, and also here's our height of our object. So we can do these, we can use these collinearity equations now as the basis for how to set up a system of equations for solving for all of those points that I showed before simultaneously. And again, remember, we're not just solving for one set of points. In general, we're going to be solving for the locations of several points. Maybe these are our ground control points, or maybe these are a subset of the points in our image, and we're going to be using all those together to solve these systems of equations. Now, in order to do that, these are actually nonlinear because of the ratio, and so there's a linearity system. Basically, you have to linearize these equations. This is a Taylor series expansion, so for those of you who've had Calc 3 or have looked at Taylor series expansions, this is just how we're doing that. And again, I'm not going to go into all that much detail on the Taylor expansion, but basically we linearize these equations, and then we can solve them for several parameters, and we may not know. So in general, if we are just looking for the x and y coordinates of the object space, that's two unknowns, we can solve for that if we know everything else, but we may not know everything else. We may not know the height. For example, here we have the height on the right-hand side, so we may not know that. We may have more than two unknowns. If we've got more than two unknowns, then we have to use additional points, and so we can linearize these equations. We put this with all of the other pixels into a set of linear equations, and we solve that linear system. And so here's our 5 images, and you can actually see that maybe we'll use the corner of a building or some other kind of well marked out points as our ground control points. We'll identify the locations of those points, and then we'll use those collinearity equations, or maybe I should say the software is going to use the collinearity equations to find that XYZ location. Now, it's important to note that the photogrammetry process is going to just assume, or it's going to require, I should say, that both the images and the objects are in a XYZ Cartesian coordinate space. And so actually it's going to solve for an XYZ location for that particular point. But then we can convert that, if we have georeferencing information for those ground control points, we can convert that XYZ location to a lat long and elevation using standard georeferencing transformations. And so the steps are, again, we identify the points that are identical in each photo and or our ground control points. We collect photos with those that contain images of those ground control points. We identify the camera image coordinates in each photo and solve the collinearity equations for the XYZ object space locations. So this is all this is the process that the software is going to go through. And so what we're going to give the software is we're going to give it our imagery. In some cases, there will be geotagging on the imagery itself. So for example, DJI drones actually include information about both camera orientation and position. That information is probably not accurate enough in many cases to do really good photogrammetry, but it's a good starting point for the algorithm. And actually these algorithms, in some cases, are iterative, and so it will use that as a good starting guess of the position of the camera and its orientation. Then, of course, we'll use our GCPs, our ground control point coordinates. We'll put those in, and the software will use those together to solve those collinearity equations, find the XYZ locations of our ground points, find our elevations, and generate those products. Orthophotos is our orthorectified mosaics. DSM, digital surface model, that's just the elevation. We can use both of these together to get 3D point clouds and generate 3D models. So that's going to be our final products from this photogrammetric process.